Thank you a lot for the introduction. So good afternoon, everybody. Thank you for being there. I want to excuse for not being there in person, and I want to take the possibility to really warmly thanks the organizer for letting me, for the comprehension and for letting me the possibility of giving online this talk. So today I would like to talk to you about, so this is an ongoing project with Inmaculada Baldomà from Barcelona, Martin Leguil from Paris, and Tere Seara from Barcelona. So let's start our, so we talk about billiards and some notion of genericity of transverse homoclinic points. So let's start our history. So the history starts back in the 70s with an article by Zehnder. This is homoclinic points near elliptic fixed points. So this has nothing to do with billiards, but what does Zehnder proves what he was interested about. So Zehnder consider a set of particular dynamics, that is, he consider some analytic symplectic diffeomorphism of the two disks. So in dimension 2 it means that your area preserving, such that you ask that the 0 is a fixed point and you will want for having some elliptic fixed point. So if you consider the linearization around the origin, you will see some rotation of angle alpha at first order approximation. And the general question that we will will clarify in a moment is how often actually do you find when you pick, like let's say if you have this set of dynamics, you pick a random dynamics inside this somehow, and you would like to you ask yourself, how often do you find transverse homoclinic points? How often in the sense of within the set of the dynamics, and also in the space, if you want, how they are distributed somehow within your disk. So let me try to make more precise the definition of transverse homoclinic point. So it's standard classical notion in dynamics, but so let's I plan to revise some standard definition. In order to define transverse homoclinic points, we will start by considering a hyperbolic periodic point P. So you have that some power Fn of your dynamics, Fn of P is equal to P, and such that you want that your the eigenvalue of the linearized dynamics at your periodic point are of modulus different from 1. And in such a framework, what is possible to define, standard notion in dynamics, is that you can define what are called the stable and unstable manifold. That is, roughly speaking, when you consider the stable manifold, you just consider all the points that in the future we will converge to let's think about a fixed point, your point P, while in the unstable case, you look at points that in the past you are converging to your fixed point P. And this set, actually, if you start with some hyperbolic fixed point, you can show that they are injective, if you start with some analytic diffeomorphism F, this set actually turns out to be injectively analytic immersion from R. So you can think of having some lines R that will somehow you are putting inside your disk in an injective way. And of course, what you could be interesting also in is that to have some local version of it. That is, you instead of looking for points that, for example, for the stable case that in the future are converging to your fixed point, you ask that not only they are converging to the fixed point, but you ask that when you look for the local manifold, that at any positive iterates, they remains at epsilon close to your fixed point. And in this local version, this has a really some manifolds. So the main difference is that here you have some nice embedding of some of R, while in this case you could a priori have something that starts to accumulate on itself. So, of course, if you want to, what I was saying here was holding for a fixed point, but it's not so different from periodic point. You just try to give the same definition, but at like all the points that are all the finite set of points that gives you the orbit of your periodic points. And so in this case, so what we mean by homoclinic point, you just have, you look at your stable and the stable manifold, and you look at an intersection of it. So in the plane, it's quite simple because you can really easy figure, like visualize the stable and the stable manifold. You are like considering some one, for example, here one-dimensional, will consider one-dimensional curve. But it's not only you. What we will be interested in not only having homoclinic point, but we'll ask to have some transverse homoclinic points. So, sorry here. Otherwise. So you want to have some transverse homoclinic points in the sense that you ask that when you consider the sum of the tangent space to the stable manifold and sum with tangent space to the unstable manifold, you want to recover the whole R2. So here from if you want to visualize, you are just since we are considering like on the plane, we're considering stable and unstable dimension that are both of dimension 1. You just want that the tangent direction to the stable manifold and the tangent direction to the unstable manifold are linearly independent. And why this kind of transverse homoclinic points are particularly interesting and relevant in dynamics, it's because like that goes back to Smale, that as soon as you have the presence, the existence of such transverse homoclinic points, you can construct in a more or less standard and canonical way horseshoe. So it means you can construct a factor with some finite subshift that assures you that your just the existence of such point gives you that the topological entropy of your system is positive. So it's like the standard mechanism in dynamics to create chaos. And if you want to think of some example where you don't have such a things, so even if I missed the talk of this morning, I think that I'm sorry. At some moment, you have talked quite a lot about integrable systems, and in such a case, actually, it's such phenomenon could not happen, and is exactly in the integrable case. It's the case where these curves, like this stable and unstable manifold, actually matches, and you have some, for example, homoclinic loop. And so, coming back to the initial question, how often do we find transverse homoclinic points? So the question that Zehnder would like to address is like to try to figure it out, to say something about the set MH. That is, you take all your dynamics F, that I remember, I recall it's all the set of analytic symplectic diffeomorphism, such that the origin is a fixed elliptic point, but such that you want that there is a transverse homoclinic points in every neighborhood of the origin. So you take, you fix your origin and you want to take any neighborhood of it, and in any neighborhood you want to be sure that it exists at least one transverse homoclinic points. And so that could if you have a dynamics and then this that belongs to such a set, it means that you could, if you want, in terms of the space, you will find actually very often transverse homoclinic points. But then the question in terms of the question could be rephrased also in terms of how, of course, this MH is contained in M, but is it big? Is it small? Would you expect that would you have some dense set? And actually, so not only it is possible, Zehnder shows that this set is not empty, but actually it is dense within the class of your analytic diffeomorphism. And so the theorem of Zehnder could be stated as follow. So up to n to m with some, I don't enter into the details, but good analytic topology, and I will insist on it that the main point and the delicate point of this is that you want to obtain this in the analytic analytic topology. This set MH that we described is residual. That is, it contains a countable intersection of open and dense subset. And so in particular, what you could, the main point is that this set that you are interested in could be described as the intersection of all the analytic symplectic diffeomorphisms that will exhibit some homoclinic transverse points in a ball centered at the origin of radius 1 over n. And then you intersect over all the possible radius, taking smaller and smaller radius. And the fact is that this theorem, actually, if you choose the good topology, and when I say that when I say that you choose the good topology, I'm saying that you want to put a topology such that your space is a bare space, so you have the bare property. The previous theorem about the density of such diffeomorphism that will present transverse homoclinic points in every neighborhood of the origin will becomes just an easy, let's say a straightforward corollary of the following theorem. That is, you fix the neighborhood, so you fix some n that will be the radius of your ball center at the origin, and you would ask that this set of diffeomorphism that will exhibit some transverse homoclinic points in the ball of radius 1 over n center of the origin is open and dense. So the fact that the property of being open is, let's say, the easy part, because you can think as soon as you have some hyperbolic periodic point which presents some transverse homoclinic point, if you do a small perturbation up to do small it enough, these transverse homoclinic points will persist. So it's something that it's let's say some robust property. And the delicate point is to try to obtain the density, and moreover the density in the analytic category. And I will try to explain a little bit the sketch of the proof of Zehnder that will be also of course the main inspiration of what we do after with billiards. So I hope that I convinced yourself, that I have convinced you that the main point is to prove that you have the density of this class Mn within the analytic topology. So let's fix some n, and so such that we have fixed this some neighborhood of the origin of radius 1 over n. So I remember to you that you can start with some diffeomorphism f on the disk, such that the origin is an elliptic fixed point. And what you can do is that, moreover, there is no loss of generality in the first step. You do a small perturbation. So the main aim now is that you fix some epsilon, and you want to do a small perturbation, a perturbation that is epsilon close in some analytic topology to your initial f, such that you are able to create some to exhibit a transverse homoclinic points within within this set B of 0 within this ball. So the first thing is that you can perturb your dynamics such that when you consider the linearization around the origin, it is conjugated to a rational rotation. And why you want to do so in such a way that you will have that your up to a change of coordinates, the differential of f at 0 is nothing but a rotation of angle 2 pi p over q, for example. And why you want to do this? Because then you can try to use some what are called some Birkhoff resonant normal form. So So I don't want to enter into details in this part, but in such a way that up to use this normal form, it is possible to show that there exists some hyperbolic periodic points that will belongs to the fixed neighborhoods that you want to work in, and for which you can describe quite well the stable and unstable local manifold. So in particular, what you could have is that so you can think of could you see my arrow?
Yes.
Okay, great. Thank you. So you can fix your neighborhood and such that you can assure that, so you have here your the origin, and you can assure that, for example, there exists some hyperbolic periodic points. And when I say that you can describe quite well the stable and unstable manifold, local manifold, it means that so you have let's say a part of this unstable manifold and the stable manifold, and the important thing is that they somehow share here some common domain, so that you can be sure that somehow you have some common domain on which they are both somehow defined. And it makes sense of how could I say, putting having that saying that the local stable manifold is above the local unstable manifold, or vice versa. And why you can do this? Because then by some simple error preserving argument, you can have, for like in an easy way, that there exists some homoclinic points. Why? So let me try to give you the idea here. So here you have to think that we have our origin. So here think of having some period-free hyperbolic points, for which you can describe quite well the stable and unstable manifold, and assume by contradiction that you don't have any homoclinic points. So it means that in particular, for example, the stable and unstable manifold, for example, the stable manifold of a point lies somehow above the local unstable manifold of the other points. But then what you can do is that you can try to, up to adding some vertical lines, you can have you can construct some pieces of some piecewise C1 even analytic curve, that is, start by considering some local unstable manifold, take some vertical lines, consider some local stable manifold, and then just move it through the dynamics. So because stable and unstable manifold are invariant, what you get is that the image of this blue line that I just draw will be something that looks like this. So you have that the local unstable manifold will be sent into the unstable manifold of the next point, and you have that the vertical line will be, of course, a little bit deformed, but then after a while you will be able to close it up, because you have some periodic points. And what you get is that since on the local unstable manifold, the dynamics is becoming bigger and bigger, when you come back to the initial point, you realize that your curve must look something like this. So there is this part, this area, that you are losing some area, because if you want, you are able to close it up, obtaining some Jordan curve, but in such a way that when you come back after a number of iterations that is equal to the period of your periodic points, you are losing some area or adding up some area, according on if the local unstable manifold lies above or below the stable one, and that contradicts the fact that you are working with diffeomorphism that preserves the area. So in the end, what it means that your stable and unstable manifold has to meet at some points. So let's say this part is like standard error preserving argument that shows you the existence of homoclinic points. But the crucial point is that what you really need is not only the existence of homoclinic points, you need the existence of transverse homoclinic points. And so let me just erase this, otherwise it will appear in the other slide. And so what you could do, so if you for a moment forget that you want to work in the analytic case, in the analytic with the analytic topology, what you could do? Actually, you have a standard way to do what you would like to do in this infinity, with this infinity topology. Why? Because here the main point is that, so assume that you have your, so far we have our, we find our periodic points, P, and we know that the local unstable manifold of P will intersect at some points the local stable manifold, for example, of F of P in some point H. And the fact is that the difficult part is that if you know, okay, you can look at the intersection points, and for example, like here, if you know that the intersection is transverse, you have nothing to do. You have a transverse homoclinic point. But the difficult part is that if you don't have something like this, and you have something that looks like, for example, if you have a point, an intersection points where the stable and unstable manifold at this point H are tangent. So the most degenerate case is that what you can think of what you have in the case of a pendulum, like for example, we have that really the stable manifold of the point will correspond to the unstable manifold of the point. So where you have some homoclinic or heteroclinic connection, but a priori this is the most degenerate case, but already for us will be like a bad configuration if you have that you have a point of tangency. And so what you could do in this case, in the case if you can allow yourself to use some just a smooth perturbation, in this infinity case you are happy because you have compact support perturbation, so bump function that could be used. And the idea is just that you look at you localize your perturbation at the pre-image of your homoclinic points, so at f-1 of H, you can find some small neighborhoods such that this neighborhood U will intersect the orbits of your homoclinic points just only at that point. And if you can do this, it means that if you can restrict yourself to do your perturbation just on this small neighborhood, you won't affect the shape of the blue line here. That is, you won't affect the shape of the local stable manifold, but you could ask to just by do a localized perturbation over here, you can modify the shape of the local unstable manifold, so the green curve, such that you can play a little bit and change the tangency of the unstable manifold at H. And so in particular, you can, keeping the point of intersection, you can just make sure that the tangency of the stable manifold is different from the tangency direction of the stable manifold. And that will create, in doing a perturbation as small as you want, a transverse homoclinic intersection. Great. So far it seems that okay, but the problem that I want to insist is that we want to do it, or the Zehnder want to do it in the analytic case. So how to do this? Because in the analytic case, you have no right, you're not allowed to use compactly supported perturbation. If you try to do something like this, you know that you are messing up with the function everywhere else. So what to do? So the idea of Zehnder goes like this. So let's try to define a function in the following way. I will define some function gamma that will consider so. You can even consider C infinity perturbation or any perturbation that are C too close to your initial, such that when you consider your perturbed system, you are C too close to your initial dynamics, and you want to arrive in R2. And how is this function defined? So you know that you start with a dynamics F where there exists some homoclinic points. The problem here is that if the homoclinic point is a tangency between stable and unstable manifold. And so you consider, now you add a small perturbation G, and you consider the perturbed dynamics that is given by F plus G, and to any G, you associated two real value. That is, when you perturb a little bit, you can follow. So you have that the hyperbolicity is a condition that is stable under small perturbation. So your hyperbolic periodic points will remain hyperbolic, and you can follow somehow the continuation of the stable and unstable manifold. So you are changing a little bit the green and the blue line, and you can, by thinking of having fixed some section that is the dashed line here, you can have a first real value that is give you the distance between the continuation of the stable and the unstable manifold. So if the G is equal to 0, this first real value will be 0, because at these vertical lines, stable and unstable manifold coincides, and so the difference between them is 0. But when you perturb a priori, you are touching the stable and unstable manifold, so you are changing it a little bit. And the second coordinates, what will be actually the distance between the tangent direction of the unstable manifold and the tangent direction of the unstable manifold. So just to give you an idea, when you consider the zero perturbation, that is just consider your initial dynamics F, in the case that you have found some homoclinic points, but which is a point of tangency, you will see that this gamma of 0 will be just 0, 0, because being 0, 0, it means that it's a point of it's a homoclinic point, meaning that the distance between stable and unstable manifold is 0, so they intersect. And if you have a tangency point, it means that when you look at the first order, so the tangency of the stable and unstable manifold, if you have a tangency, the distance between the tangent space is also 0. So if you start in the bed configuration, you will have that this gamma at 0 will be 0, 0. And our aim is to find, but not in this infinity, but in the analytic case, something that a perturbation for which actually what you want to realize, your aim will be to realize that to find a perturbation such that you can realize the value 0 lambda, for lambda small in eventually very small but different from 0. And so how to do this? So there are different, the idea is that you come back to like an application of the implicit function theorem. Why? If you are able to show that this gamma is not only Frechet differentiable but also C1, so the standard idea is that you go for calculating the Gateau differential and check the Gateau differential is continuous with respect to the points. If you can do this and you can assure that when you consider the differential of this gamma at 0, when you restrict to some just a smooth perturbation, this is surjective. That is the case because thanks to the fact that we are in restricting ourselves to C infinity perturbation, you know that we are allowed to use compactly supported function, and so you can change the shape of your stable and unstable manifold as you wish. And so in particular, you can realize any value of this first order. So this gamma is like a 0 and first order approximation of the distance between stable and unstable manifold. But then if you can put this together, thinking of this gamma defining, so if you show that is C1 Frechet differentiable like restricted of among all possible perturbation, it means that by the continuity of the differential, we will have that this differential will be still surjective also if instead of restricting yourself to C infinity perturbation, you restrict yourself to analytic perturbation. And that's the main point. If you can show that it's surjective restricted to analytic perturbation, then you can try to, you can apply like implicit function theorem, and you know that you will consider some function that takes some g, that will be some analytic perturbation, some gamma, and you look for this gamma of g minus 0 lambda. And up to choose lambda small enough, which is but different from 0, which would be possible, actually you will be able to find some analytic perturbation whose image will be exactly by this gamma 0 lambda. But then, meaning that you have an image which is 0 lambda, it means that you have an homoclinic point, because the distance is 0, but that is moreover transverse, because the stable and the stable direction are at a positive distance, if small, but okay. So far this is the main ideas, the sketch of the proof of Zehnder, and our the project with Imma, Martin, and Tere was like, okay, could you do the same things but for billiards? And the main difficulty is that now, so if you try to go along the proof of Zehnder, so one of the main points is that now you are you know that you can change the shape of the stable and unstable manifold because you are allowed to use some compactly supported function. So in particular, you're allowed to change your dynamics on a small neighborhood, but in such a way that you are touching you are meeting the orbit of the homoclinic point just at one point. If you want to do this for billiards, the idea is that now I will recall the billiard dynamics in a moment, even if, or I think that today you have already heard it. But the main point is that now the perturbation that we allowed ourselves, you want to perturb the table and not the dynamics. But if you perturb the table, so I think you have some circular table, and then you can try to play a little bit like changing the shape of the table. Any such perturbation will affect the dynamics in a fiber way. That is, if you do the perturbation on the table, in the dynamics you will have a perturbation that will affect a whole vertical strip, and so it will be. But I will be back in a moment on this. So let me start by recalling how we play billiards. So I will consider some domain in R2 that is strongly convex. So I want that the curvature is positive. So you can think of smooth. In our case, actually, we will want to do it analytic, but and what you do, you fix some gamma that is an arc length parametrization of the boundary of your domain, such that if you take some S that is in the one-dimensional torus, you can associate to it some gamma of S that is telling you at which points on the boundary you are. So your gamma of S lives on the boundary of your domain. And once you have chosen the points on the boundary where you are, if you want to play billiards, what you have to do is that you have to choose the direction at which you shoot your ball. And so it means that you have to choose an angle, phi, that will belongs to the interval minus p over 2, that is the angle that your trajectory have with the inner normal at gamma of S. So here I use the inner normal. Sometimes in the literature you have that it's more stated in terms of the angle with the tangent direction at gamma of S, but it's different of p over 2, so not so problematic. And so what is the dynamics that you associate? So once you have when you choose your points S and your angle phi, what you do is that you go at gamma of S, you shoot with your fixed direction determined by phi. You go along a straight line, and you consider the points when you meet again the boundary of your domain that will give you some other points gamma of S prime, and you will arrive with some angle that will be phi prime. And the fact is that in standard Birkhoff billiards, you can continue to iterate your dynamics because you ask that the angle of incidence is the same as the angle of reflection, and so you just reflect with respect to the tangent direction, and you restart with the same angle, and so that gives you a way to define some discrete dynamics. And what we can say about these dynamics, so of course it's so if we start with a smooth boundary, it will have some smooth diffeomorphism that will preserve the orientation, and also it preserves some area form on the annulus. And moreover, this F is has the property of being a twist map. So it means in particular that like from if you want to try to visualize it, if you consider some vector, some vertical segments, and you look at what is the image by our dynamics, in order to be precise, you have to go for a lift of your dynamics, or on R times the minus P over 2. What you get is that this segment will have the vertical segment, once you consider its image through your dynamics, will be a graph. And so in particular, and the idea is that if you come back to what happens in the billiards, is that if you take a vertical segment, it means that you are starting at the same points, but you are shooting with different angles. And the idea is that if I shoot with a bigger angle, I will meet my boundary at a point that is more far with respect to that to a smaller angle. The property of being, so in particular, the possibility of having this twist property, it becomes really interesting because it means that you can somehow, philosophically, it is telling you that the dynamics could be simplified in the sense that you are, instead of having something that is two-dimensional, you are lots of feature of dynamics of homeomorphism on the circle, so one-dimensional, that could play a crucial role in order to describe your maps. So in particular, it's possible somehow to define some rotation number of points. So you do what you would expect to do in the case of, for example, homomorphism of the circle. That is you can consider your points. You can consider some iteration, the n iteration of the lift or your map, and then you project on the first coordinates, and then up to consider so the difference with respect to the initial coordinates, and divided by n. If you take the limit for n goes to plus infinity, for almost every point, you will obtain some rho. And actually, by fixing the value of this rho, you could find some interesting orbits that are some interesting orbits that are what I call that defined the Aubry-Mather sets. So let me come back a little bit to try to state at least our result. So something that plays roles that I put a little bit under a rug in presenting you Zehnder's statement is the topology. So the main point is that we want to be able to talk about residual sets. So in particular, we have to think about choosing a topology that will have the Baire property. And in order to do this, we will consider the set of analytic function gamma. So we will play with the set in which we are we want to put ourselves. We consider the parameterization of the boundary. So we consider analytic function gamma that goes from the one-dimensional torus to R2, that you can assume that we can extend it to a complex strip of height some fixed R, and that they are bounded. And what you get is that if you consider this space of this set of function, and you put on it the supremum norm of the complex strip of weight R that is fixed, this is a Banach space. And so in particular, if you have a Banach space, this is a Baire space. And so we can try to, in particular, once you have a countable intersection of open and dense set, it will remain in particular a dense set, and so it simplified the proof as done in Zehnder. And so what are the set of billiards table that we consider? It will be the set of gamma, so of parameterization that are in that are this analytic function that could be extended on a complex strip of weight R, such that these gamma are embedding, and we ask that the image is strongly convex. So it remains, it will be, this set is an open set of a Baire space, and so it remains in particular a Baire space. Just to give you some more details about the topology that we want to do. So the idea is that our aim is to show that within this topology, there is a dense set of billiards, so of such gamma, such that you will have plenty of transverse homoclinic points. And so our theorem, so the main results goes like this. So fix some R positive, that will be the weight of the height of the complex strip that we want to consider. And then there exists a Baire generic set that is contained in set B of R that we just described, such that if you take any gamma in this set, you can think of looking at the billiard map that is associated to such a table, to the billiard table gamma of T, and that billiard map will have a hyperbolic periodic points of rotation number P over Q with a transverse homoclinic points for any rational P over Q in 0, 1. So that is to say, you can choose the rotation number that you want, and if you want the rotation number in terms of the billiard table becomes, you can visualize it quite easily, because if you have like a rotation number of P over Q, Q is the period of your periodic points, and P is telling you how many turns of the table you are doing before closing up. And so this is telling you that actually you can find plenty of you can find plenty of transverse homoclinic points, where now instead in Zehnder's results, like the plenty of the how often in terms of the space was determined by in any neighborhood of the origin, and here the how often in terms of the space becomes in terms of for any rotation number. You can find some hyperbolic points with a transverse homoclinic points associated. And so, as in Zehnder, because of the fact that we are working, we put ourselves in the framework of working in a Baire space, so we have the Baire property, and in order to prove this result, it is enough to prove it the following one. You can fix the rotation number that you want. You can fix any rotation number, and you must show that you can find a set, so within the set of admissible tables, that is this BR, whose billiard map associated to the billiard table gamma of T as hyperbolic periodic points of rotation number P over Q that you are fixing with a transverse homoclinic point, and you want to ask that this set is open and dense. Once again, the openness property is somehow the easy part, and the the more delicate part is about the density, once again, within the analytic category. And so let me also, so I don't have, I think that I have still 5 minutes. So I could, there are some previous results about, of course, genericity, about transverse homoclinic points in billiards, but were more as far as we found in literature, were more about some C2 genericity or C3 genericity. Let me also highlight a recent result about the density of convex body presenting some hyperbolic set also in higher dimension. And so the things that I want to emphasize is really about the fact that the delicate part is about the doing this in the analytic setting. So a useful something that becomes quite useful comes from the Aubry-Mather theory. So what is the Aubry-Mather theory? So when you have a twist map that is area preserving and you fix a lift, it's possible to define actually to describe the dynamics in terms of some generating function. And in the billiard case, your generating function will be nothing but the Euclidean distance between two successive bounds. And so I skip the details because I'm running out of time here. But once you have this generating function, what you can think of is that the study of your dynamics can be described in terms of variational problems. So you can define some formal infinite functional such that what you will be interested in is you will look for some minimizing orbit, some orbits that will minimize your action functional. And so let's say this the Aubry-Mather sets are exactly the segments, the orbits that will minimize such a functional. So that could be obtained from from a variational setting. So let me, what I would like to say is that, so if we denote by M the set of all this minimal configuration, to any of this minimal configuration, you can associate a rotation number. And the main point is that that is a theorem, so that it's the fundamental theorem in this Aubry-Mather theory that goes back to Aubry-Mather, Bangert, and so on, that if you can choose any rotation, any alpha in 0, 1, and it's possible to show that if you consider orbits that minimize your actional functional with a prescribed rotation number, that set will be non-empty. And so in particular, when you focus yourself on considering a minimal configuration with a rational rotation number, it tells you that you will always find some periodic orbits that will arise as a minimizing configuration. And the main point is that when you fix some rational rotation number and you consider the set of minimal configuration with that prescribed rotation number, what you find inside this set is that, of course, you will find some periodic orbits, but it's not only this. What you will find inside this, you can always find also some heteroclinic points. So it means that you will have some points that will belong, let's say, if for a moment forget that you don't have any hyperbolicity, but let's say in the future will go to some periodic orbits that will belong to this first set, and in the past goes to another points in this within the set of periodic minimal configuration with prescribed rotation number. And the idea is also, because of the billiard map is a twist map, if you fix any rotation number, you are sure that you can find a periodic orbit with that rotation number. And moreover, you can find always some points that plays the role of some heteroclinic connection that between two periodic orbits. So, like for example, if you think of the pendulum, you have something. You have some hyperbolic. You have a two periodic that. Here, for example, this is a portrait, the face portrait of the an elliptic table. What you have is that you will have some two periodic hyperbolic points. That is the yellow one, and you have that the upper matrix will play the role of this M plus that was described before, while the lower matrix will play the role of this M minus. And the important thing is that here, for example, if you forget the blue lines, and so you restrict yourself just to these periodic orbits and this, let's say, positive heteroclinic connection, this set has some good property that is you have some total order on it. And so in particular, it means that if you just keep track of this set and you see it on the annulus, once you project on the base, on the first coordinates, you will have a partial graph. That is, the projection on the base point is injective. And so if you are injective, what it means is that if you restrict yourself to this set, if you start to take vertical strip, unless you can take a vertical strip that is thin enough, you can be sure that you will have just one point of an orbit of, for example, some homoclinic or heteroclinic orbits. And so I think that I'm running out of time, but so let's just to give you the idea, the rough idea, I'm almost finished, the sketch of the proof of our theorem. So what we have to do, we are fixing some billiard table in our good set. We are fixing some rational rotation number, and the aim is to find some other billiard table that is still analytic, but this be very close, even in the analytic topology, to our gamma zero, such that this perturbation will have some hyperbolic periodic point of rotation number p over q with a transverse homoclinic intersection. And so putting together the ideas of Zehnder, and that also some ideas that goes back to Genericity and this Aubry-Mather theory, first thing is that you can find some periodic points of rotation number p over q in a unique way, because eventually up to perturb it, you can also assure that there is just one periodic points in this set of minimal configuration minimal configuration of periodic orbit. And so in particular, it will have a point in this what I called M plus, and up to perturb a little bit again, but as small as you want, you can assure that you will find just one periodic point, one periodic orbit that moreover is hyperbolic, and the point that this belongs to, that comes from Aubry-Mather theory, that belongs to this M plus, moreover is some true homoclinic points, because it will be like it will belongs to some stable manifold of some f of p and the unstable manifold of p. And if you have now this Q that is, if it's transverse homoclinic points, you are done. If not, the main point is that maybe it's, as in Zehnder case, you have a point, an homoclinic point, and maybe the problem is that it's a tangency point. And so now, the perturbation that you are allowed, it's a perturbation of the boundary, and how it affects the perturbation on the dynamics. If you try to do even compactly supported perturbation on the boundary, what you get is that your dynamics will be fiber-wise perturbed. That is, okay, you can perturb your dynamics in a very thin strip, but it's a vertical strip. There is no way you are touching all the vertical above your above the compact set on the table that you are perturbed. But now the main point is that since now we have working with this Aubry-Mather theory, because we have this totally ordered property, what you know is that the homoclinic points that we have found here, it's good enough in the sense that since its orbit project injectively on the base, you can find some small vertical strips such that you are sure that there will be just one point of the orbit, of the homoclinic orbit in your strip. And so you can redo the same trick as Zehnder, because now you know that if you do a perturbation, even it's a perturbation of the vertical strip, you are just touching the orbit at one point, and so it means that the orbit, the shape of the unstable manifold at your point, at your homoclinic points, of the green, of the stable manifold, the green one, isn't touched at Q, because it should be, if you want to modify it, you have to modify it at along points of the orbits of Q, and it's not the case. And you know that you are touching in a controlled way, you are changing in a controlled way the shape of the unstable manifold, that is the yellow curve at Q, because you just want, you're intersecting the orbit of Q just at one point. And so you can do the same trick. And again, what you have to do is that you construct this, as before, this function gamma that gives you this, it's defined on the whole set of perturbation taking value in R2, that is giving you the distance between stable and unstable manifold at your homoclinic points, and the distance between the tangency direction of the stable and unstable manifold. You show that it's C1 Frechet differentiable. You show that the differential at 0 restricted to smooth perturbation, so compactly supported perturbation on the boundary is surjective. Even if you restrict then, because of these two conditions, you know that the differential will remain surjective also when you restrict to analytic perturbation. And then, so I will, and then what you can do is that you can up to passes through some truncated Fourier series. You can redo the final step of the Fourier of the Zehnders proof. That is, you can do some implicit function theorem and assures that you can do a small perturbation of the billiard table such that you obtain a transverse homoclinic point, that what we were associated to the hyperbolic periodic points with the prescribed rotation number. And I thank you for your attention. And sorry, I probably have run out of time, but it's.
Thank you.